Okay, so for this second example, we're going to take this generic second order ordinary differential equation and we are going to perform the finite difference method in the same way that we did the previous example. And there's going to be a few differences, but we'll start off with this first one right here. We're going to come up and say that this one is going to be u I plus 1 minus 2 ui plus ui minus 1 all over delta x squared. Okay, that's nothing more than doing the algebraic equivalent of this first term. Then we're going to do 6. Now we just have a first derivative, so this is going to be ui plus 1 minus ui divided by delta x. Okay, and so recognize that this is nothing more than the forward difference approximation for a first derivative. And for purpose of this class, we'll make the assumption, and I'll try to remind you during the final exam, that if there is a first derivative inside a second order ordinary differential equation, that you should use the forward finite difference approximation, although you could use the backward and center difference approximation as well. Anyway, and the last term is going to be nothing more than ui, and that's going to be equal to 2. And then we need to multiply all these equations by delta x squared so we can kind of put it in a format that makes sense. Okay, and so we're going to multiply the left-hand side all by delta x squared and the right-hand side by delta x squared. Okay, so I'm going to come back down here. So in the first term, well, we're going to be left with nothing but ui plus 1 minus 2 ui plus ui minus 1 plus 6 delta x ui plus 1 minus 6 delta x ui minus delta x squared ui equals 2 delta x squared. And now we just need to group some terms together. So we're going to take the ui plus 1s first of all, and that's going to be 1 plus 6 delta x ui plus 1. Then we're going to take all of these, let me do doubles for the ui's. So we have a minus 2 for this one. We have a minus 6 delta x for this one right here. And we have a minus delta x squared for this one right here. This is all times ui. Okay, so this is a plus right there. And the one remaining one is this one right here, so we'll just do plus ui minus 1 equals everything on the right hand side, which is 2 delta x squared. Alright, we'll keep this one as our c, and then we'll define this one as maybe our d, and then we'll keep this one as our b. Alright, so now that we have this, let's go off to MATLAB, and we will use our code from before and try to convert what we did with the previous example into this example right here. If it wakes up. Okay, well, I've got a different problem, so let me just go over here and I'm going to do a control A. And I'm going to come over here and do a control V, and I'll clear my window right here. Okay, and this is no longer an example for the temperature rod, so I'll just remove that one. You'll notice then that I've got an example 2 right here already set. I'll hit control S to save it. Let's just go through this. We don't necessarily need some of these things. For example, we don't have the coefficient for the convection coefficient. We do have a dx. Let's go take a look at our problem. Down here it's 0.1. We're not worried about t's anymore, but we are worried about u's. So I'm going to change it to be u lower, and I'm going to come here and change it to be u upper, or the right side. Okay, let's take a look at what the values are. So we have u at the lower side, when x equals to 0 is 10. And we have u at the upper side, or the right hand side, which is 1. So there's going to be some sort of function that starts at 10 and goes down to 1. Alright, then we have to form these other constants that we defined right here in this algebraic expression. We have c, so let's go off and do c. Let's manipulate it here, and I had a minus 2, then there's a minus 6 times dx. Oops, let's make sure it's a times. And then there was a minus delta x squared. Okay, so that whole value is going to be a c. Okay, and of course I can pull the negative sign out, but I left the negative signs inside the definition of c. Alright, I need to update my b. It's nothing more than 2 times dx squared, and then I define this new term that's in front of the ui plus 1 unknowns. That's going to be a d, and I set it to be 1 plus 6 times dx. Alright, so we're working our way down. Let's talk about the x vector. We are still going to define the x vector with a dx of 0.1, but not going from 0 to 10 now. It's going from 0 to 2. Let's change that from 0 to 2. Okay. We can set up our empty matrix. It's going to be the exact same. It's going to have the same size squared as the x length vector right here. Our b side is going to be defined here. We have some known quantities in the upper left and bottom right corners, or the first rows and the last row. So this is always going to be the same of 1 and 1. Okay, it's going to be using these little equations right here. Now we need to adjust TL and TR. These are not defined anywhere. We actually have UL and UR defined, so that works out really well. And now we need to update variables inside our matrix. So we don't have a negative C anymore. We actually have a C. Okay, so we need to come in here and update C to be all the diagonal terms except for the first and the last rows. Okay, we need to go back 1. If we go back 1 value in terms of x, we are just left with 1 for the coefficient for all of those terms. And if we go forward 1, well, we actually have d as our coefficient right there. So we set that to be d. Our b side vector looks like it's okay, assuming that, of course, we define our little b up here accordingly, and hopefully it's 2 times delta x squared. Okay, and then we need to do the same sort of thing, but in this case we don't care about t's, we want u's for all values of x across the domain, so we change that to be u. I need to change this to be u, and this to be u, and this to be u. Alright, and if everything's good, we can hit Control S and run it. And I pull the figure in, and sure enough, we have a function, which is the solution to an ordinary differential equation. It's u, and it's approximated using the finite difference method, and it starts off at 10, and it goes all the way to 1, and these are the values in between across the unknowns, all the way from x0 to x, probably x20 or x21. We can take a look at the size of it if we want by typing in n. Yep, 21. Okay, and so there's actually 21 unknowns, except the first equation right here and the last equation are trivial, such that there really are 19 values that we wanted to solve for, but we can solve for, of course, the 20th and the 21st unknowns if we pop it into our first and our last rows of our matrix. Last thing we're going to do then is just kind of increase, or rather, increase the resolution and decrease dx. So I'll come in here and just make dx to be 10 times smaller. I'll hit run. And after a few seconds, the figure pops up, and now we can see that we have 10 times as many points and unknowns, and we've got a nice smooth curve. Okay, we don't have the equation of the solution. That's going to be the analytical solution, but we do have a really good numerical solution, and it's good enough to approximate the solution in a lot of ways without ever having to do any sort of diffie-q sort of calculations using inverse Laplace transforms and other things that you may or may not know yet, but you will later in Mechanical Engineering 335.